What is cosmic inflation? At the very beginning, our universe went through a period of exponential faster than the speed of light stretching of space, known as inflation. The stretching was caused by a repulsive form of gravity, and the universe doubled in size at least 100 times, going from the size of a billionth of a proton to the size of a grapefruit. Inflation ended when the repulsive energy decayed into ordinary matter and energy, at which point ordinary Big Bang expansion took over. Why do we believe inflation happened? The theory of inflation explains two properties of our observable universe. 1. The uniformity of space, and 2. The apparent flatness of the universe. The observable universe. The observable universe, as the name indicates, is a universe that we can observe from Earth. That is, light from the contents of the observable universe has had time to reach our instruments on Earth. Assuming that the universe is the same in all directions, the distance to the edge of the observable universe is the same in every direction. So the shape of our observable universe is a spherical ball with the observer at its center. Inflation explains the uniformity of our observable universe. At the largest of scales, the observable universe displays an extraordinary level of uniformity. There are, of course, distinct structures in space, such as galaxies and stars. However, from a distance far enough away, all of space seems to look the same from all directions, similar to how sand in a desert will appear uniformly distributed if observed from a plane flying high up enough in the sky. The theory of inflation allows the contents of the baby universe sufficient time to interact and come to a uniform density of energy and temperature before the rapid expansion occurred. It is that uniformity which is the present uniformity of space we observe today. Without inflation, the Big Bang model would not have given the baby universe enough time to reach uniformity in this way. Inflation also explains the flatness of our observable universe. Space-time incorporates the three dimensions of space, up and down, left and right, and back and forth, and the fourth dimension of time. General relativity describes how mass and energy can curve space-time, and accordingly, the mass and energy of the universe can also curve space-time. There are three possible curvatures the universe could have: positive curvature, negative curvature, or no curvature at all, i.e. be flat. The critical density of the universe is the mass and energy contained per unit volume of space needed for a universe to be flat. That means the gravity produced by the mass and energy in the universe is such that it perfectly balances out the stretching of the universe. When the universe has critical density, it continues to stretch at a decreasing rate forever until infinite time has passed, whereupon the stretching will finally halt. But as we all know, infinity has no end. The density parameter. The density parameter, symbolized by the letter omega in the Greek alphabet, is used to determine what curvature the universe has. It is the average mass energy density of the universe divided by the critical density. If the density parameter is more than 1, there is positive curvature. If the density parameter is less than 1, there is negative curvature. And if the density parameter is exactly 1, i.e., the average mass energy density of the universe is the same as the critical density, then the universe is flat. For the universe to have positive curvature, there is enough mass energy density in the universe to produce gravity that will warp space-time enough to eventually overcome the stretching of space, so that the universe will collapse back in on itself to form a closed universe. For the universe to have a negative curvature, there is not enough mass energy density to produce enough gravity that can halt the stretching of space, so the universe will be an open saddle-shaped universe which continues to stretch forever at a decreasing rate. And we have already covered that in a flat universe, there is just enough mass energy density to produce gravity that perfectly balances out the stretching of space. What do we mean by a flat universe? When describing the universe as flat, it is not meant that it's flat in the same sense as a 2D shape is flat, but rather that the geometry of the universe is such that parallel lines will never cross, the angles in a triangle will always add up to 180 degrees, and the corners of cubes will always make right angles. In a closed universe, the angles of a triangle would be more than 180 degrees. In the open saddle-shaped universe, the angles of a triangle would add up to less than 180 degrees. And in the flat universe, as mentioned, the angles of a triangle would add up to exactly 180 degrees. Why do we think the universe is flat? We can calculate the density parameter of our universe using two methods, and both methods indicate that it is very close to 1, therefore suggesting that our universe is very close to being flat. The first method involves counting up all the mass energy in the universe, taking its average density, then dividing that average by the critical density. The second method involves drawing a massive imaginary triangle on the cosmic microwave background radiation and seeing if the angles of the triangle add up to 180 degrees. The cosmic microwave background radiation, also known as the CMB, is the oldest light in our universe that has traveled to our instruments. As the photons of light traveled across the universe, their wavelengths stretched, transforming the photons into microwave radiation. When the imaginary triangle was drawn on the CMB, it turned out that the sum of its angles did indeed add up to 180 degrees, indicating that our universe is indeed flat. How inflation explains the flatness. Before we get too excited and state definitively that our universe is flat, we have to remember that the exponential stretching of space brought on by inflation drives the universe toward flatness, smoothing out the fabric of the universe. We can only measure the observable universe, which may be part of a much larger universe which might not be flat. The analogy that is often used is how an ant sitting on the surface of a large inflating balloon would assume that the surface it is sitting on is flat, because that's how it would always appear to him from his tiny perspective. We may be that ant, and the universe is so massive that whatever we can measure will appear flat to us. And that, in a nutshell, is cosmic inflation. As always, I hope you enjoyed this video, and please remember to subscribe to LondonCityGirl for more informative and educational videos from me.